In industrial facilities, many operations depend on heating or cooling process fluids. For example, the liquid entering this distillation column is heated to enable the distillation process to occur, while this process liquid is cooled so that it can be properly stored. This heating and cooling is done by transferring heat from one fluid to another in devices like these called heat exchangers. To understand how heat is transferred, it's important to understand what heat is. Heat is a form of energy that's associated with the movement of molecules in a material. This energy can often be measured as temperature. For heat transfer to occur, there must be a difference in temperature. When there is a difference in temperature, heat is transferred from the material with the higher temperature to the material with the lower temperature. Heat can be transferred between materials in three basic ways: by conduction, convection, and radiation. With conduction, heat is transferred as a result of physical contact between two materials, or from one part of an object to another part of the same object. Another form of heat transfer is convection. Convection is the transfer of heat within a moving fluid. Convection can be divided into two categories: natural convection and forced convection. We'll use this container of water and dye to show how natural convection works. As the water is heated, the water that's closest to the bottom is heated more than the water elsewhere. As the temperature of the water on the bottom increases, that water becomes lighter or less dense and rises upward. At the same time, the cooler water sinks to the bottom of the container. So during natural convection, as heat is transferred to the water, the difference in densities causes the water to circulate in the container. This circulation helps to transfer heat throughout the water. During forced convection, heat transfer occurs when a mechanical device such as a pump or a fan causes the fluid movement. In this process, air is being moved through the heat exchanger by a fan. The third form of heat transfer is radiation. Radiation is the transfer of energy by electromagnetic waves. Microwaves and light waves are examples of electromagnetic waves. When electromagnetic waves strike an object, they may be transmitted through the object, reflected off the object, or absorbed by the object. If a wave is absorbed, its energy is transferred to the object and the temperature of the object increases. In a typical heat exchanger, heat is transferred by conduction, convection, and radiation from one fluid to another. As a general rule, most heat transfer occurs by conduction and convection. To get a better understanding of how heat transfer occurs in a heat exchanger, we'll use this heat exchanger. It's called an air fin cooler, or a fin fan cooler. It's used to transfer heat from a process fluid to the air that flows through the cooler. The cooler consists of a series of tubes, each of which has thin metal fins. The heat exchanger also has a fan. During operation, the fluid being cooled passes through the tubes. The fluid transfers heat to the tubes by conduction and convection. Some of this heat is then transferred through the tubes and into the fins by conduction. From there, heat in the tubes and the fins is transferred by conduction and convection to the surrounding air. To increase the amount of heat transferred to the air, the fans in the cooler can be started. This increases the airflow through the cooler, which increases the amount of heat that is transferred by convection to the surrounding air. For example, as the difference in temperature between the two fluids in a heat exchanger increases, the amount of heat that can be transferred also increases. The amount of surface area in a heat exchanger is another factor that affects heat transfer. Basically, the greater the surface area, the greater the amount of heat transfer that can occur. Another factor that can affect heat transfer is the type of material that the heat is transferred through. Materials that are more dense are better at transferring heat and are normally used as conductors of heat. On the other hand, materials that are less dense will transfer less heat and are normally used as insulators. The flow rates of the fluids involved also affect the amount of heat that can be transferred. Generally, as the amount of fluid that passes through a heat exchanger increases, the amount of heat that can be transferred also increases. Heat transfer can also be affected by the presence of contaminants in the fluids. These contaminants, or impurities, can build up on a heat exchanger and form another layer of material that the heat must transfer through. This layer of material will act as an insulator, and the amount of heat that can be transferred in the heat exchanger will decrease. In this topic, we talked about heat and heat transfer, and we looked at how heat can be transferred by conduction, convection, and radiation. We also looked at how heat is transferred inside a heat exchanger, and we discussed factors that can affect heat transfer. As an operator, you may be required to operate many types of heat exchangers. Since shell and tube heat exchangers are one of the most common types of heat exchangers, you need to be familiar with their components and operation. We'll use this illustration of a shell and tube heat exchanger to explain how it works. The main components include a shell, a group of tubes called a tube bundle, tube sheets, and heads. The shell is the casing of the heat exchanger. The area inside the shell and outside the tubes is commonly called the shell side of the heat exchanger. The shell also has an inlet and an outlet. The tubes are used to create a separate flow path through the shell. Each end of the tubes opens into a head. One head directs flow into the tubes, while the other head directs flow out of the tubes. The area inside the tubes and heads is called the tube side of the heat exchanger. The heads also contain a tube side inlet and outlet. The ends of the tubes are supported by the tube sheets. The tube sheets also isolate the heads from the shell side of the heat exchanger. The tubes are supported inside the shell by partitions called baffles. The baffles also direct flow through the shell side of the heat exchanger, which helps increase the efficiency of the unit. Here's how this heat exchanger works. During operation, the cooler fluid enters the shell, flows around the tubes, and leaves through the shell outlet. On the tube side, the hotter fluid passes through the inlet head, through the tubes, into the outlet head, and leaves through the tube outlet. As the hotter fluid passes through the tubes, it transfers heat to the tubes and the fluid on the shell side, so the temperature of the fluid flowing through the tubes decreases. On the shell side, the cooler fluid passes around the tubes and receives heat from the tubes, so its temperature increases. This is a simplified illustration of a distillation system. The heat exchanger in this system is used to cool the process liquid so that it can be stored safely. In this system, a distillation column is used to separate a product from a process liquid. The product boils off and leaves the top of the column. The remaining liquid is pumped from the bottom of the column. The hot liquid passes through the heat exchanger and transfers some of its heat to a coolant that flows through the shell side of the heat exchanger. The cooled process fluid is then sent to a tank where it's stored. In this system, the heat exchanger is used as a heater. The process liquid that's pumped through the heat exchanger tubes is heated by steam that flows through the shell side of the heat exchanger. The heated liquid is then sent to a process reactor. In the reactor, additional materials are mixed with the liquid, and a chemical reaction occurs. By heating the process liquid, the heat exchanger enables the chemical reaction to take place more efficiently. In order to get fluids into and out of a heat exchanger and make sure that heat transfer occurs efficiently, some auxiliary components are needed. These auxiliary components include valves, instruments, and steam traps. There may be many different valves used with a heat exchanger. For example, isolation valves may be located on a heat exchanger's inlet and outlet. They're open to place the unit in operation and closed to isolate the unit when it's taken out of service. Many heat exchangers also have drain valves. These valves are used to remove fluid from the heat exchanger when the unit is shut down. Vent valves are also found on heat exchangers. Vent valves are used to remove air or other undesirable gases from heat exchangers. If pockets of air or gas are trapped inside the unit, they can prevent process fluids from coming into contact with some of the tubes. When this happens, the heat exchanger won't be able to transfer heat properly. These pockets reduce the heat exchanger's efficiency and can produce hot spots. A hot spot is an area in the heat exchanger where temperatures become excessive. These areas of high temperature can damage the heat exchanger. Another valve that's commonly found on a heat exchanger is a relief valve. Relief valves are used to prevent overpressurizing heat exchangers. If the pressure exceeds a preset limit, the relief valve opens to relieve the pressure. The relief valve will remain open until the pressure falls below the preset limit. Another type of valve that is commonly used with heat exchangers is a control valve. Control valves are used to regulate the flow of fluids through heat exchangers. For example, the flow of the heating or cooling fluid is often regulated to control the temperature of the process fluid leaving a heat exchanger. In this system, the control valve is linked through an instrument system to a device that senses the outlet temperature of the fluid. As the fluid's temperature changes, the sensing device sends a signal through a controller to the control valve actuator, which opens or closes the control valve and regulates flow to maintain the desired temperature. Generally, an operator can observe instruments to determine if a heat exchanger is operating properly. These instruments are often located in the control room, but they may also be found on or near the heat exchanger. Depending on the heat exchanger and its use, pressure and temperature gauges may be placed on any or all of the heat exchanger's inlets and outlets. On heat exchangers that use steam, an auxiliary device called a steam trap is often used. The steam trap drains water or condensate from the steam in the heat exchanger without letting the steam escape. Lost steam reduces the efficiency of the heat exchanger.